Hi, in this video, we want to look at different ways to get correlation measurements in R. Okay, so I'm in a situation that I want to check, is there a correspondence between some columns of data that I have? All right, very typical thing that we'll be doing when we're doing like predictive modeling or maybe factor analysis or structural equation modeling. A lot of things in psychometrics use this. Supervised learning will use this. There's a bunch of cases where this will be really important for us. Now, if you just go through introductory statistics, you really just talk about like one type of correlation usually, and that's Pearson correlation. And that only works when I have two numeric variables. Now, what we want to do, we want to look at other options, including ways that we can get correlations between other types of data. All right, so there are multiple ways to measure the correspondence or correlation between two columns of data. And what we're going to do, we're going to dig through a couple that we have in R. All right, so I made a table that summarizes the major ones that I feel like are really worthy of being highlighted. So our correlations that we have are Pearsons, Spearman's rho, Kendall's tau. Then, so all of these are appearing in base R. The remaining ones that I'll talk about are in the psych package in R, and how all of these work is that they take categorical or ordinal data or actually I should say, let me reword that, binary and ordinal data, makes the assumption that data is coming from, that data is binned data from normal distribution data, and then uses that normal assumption to use to get a maximum likelihood estimate of the Pearson correlation. So there's a lot going on with these, and I'll reiterate this as we go through. All right, so the first one is Pearson correlation, and this is the most important one, most well known. When most people say correlation, this is the one they're talking about. This can handle numeric data, so ratio and interval. To do this, I just go ahead and use the core function in base R, and this is actually the default one. So if I don't put a method in there, it will automatically go with Pearson. If I want, I can actually specify Pearson if I like. And this is straight line correlation. This is a good choice if I'm doing linear regression. This is also fast. This is probably the fastest correlation we got going on. The next one is Spearman's rho. And now this one can handle numeric data and ordinal. To get this, it's just like with Pearson, I use the core function, but now I put method equals Spearman. And now how this works is that it takes the data, it ranks the data, and then it runs Pearson's correlation. There's a little bit of nuance in there in how it handles ties that I'm skipping over, but that's the big picture. Take the rank of the data, run Pearson's correlation on the rank. All right, so in general, Spearman's rho will be a little bit larger than Pearson's measurement of correlation, not by much, and it may be less, but usually in my experience, almost always, not 100%, but nearly 100%, Spearman's rho gives a larger correlation than Pearson's correlation. All right, Spearman's correlation is a good choice when I believe that there is like a monotonically increasing or decreasing relationship between the two variables. Now, Kendall's tau, what this does, this measures the concordance between the data. And this has a kind of a combinatorics flavor to it. This is a good choice when we're working on conditional probability models. Now, this can handle ratio, interval, ordinal, and binary data. So this is a very good choice when I have more complicated data sets to work with and wider range of data types. And to run this, I'm going to set method equals Kendall and just run the core function just like before. All right, so these first three are in base R. Now, the next four that I'm going to talk about, these are in the psych package. You notice I'm using double colon notation over here. And what these do, these take dichotomous or ordinal data, makes the assumption that the data is bin data from normal distribution, then uses that normal distribution assumption to get a maximum likelihood estimate of the Pearson correlation. All right, so remember that when we look at these, there's an assumption of normality under the hood, and it's using that normality to get a maximum likelihood of the Pearson correlation. All right, so the Terracork correlation works with two dichotomous variables. It's in the psych package. And so what this is doing, we're taking basically a 2x2 contingency table and making the assumption that we have bivariate normal, and we've binned those the bivariate normal data into a 2x2 grid, and then under that assumption works out the details using maximum likelihood estimate. Now polychoric, this takes two ordinal variables. It's in the psych package, and now here it also assumes that the data is binned from bivariate normal. And so if I have an n by n contingency table being built by the two ordinal variables, it assumes that the first one is binned into n groups from the normal distribution observed data, and then the second one, which is also assumed to be normal, is binned into m bins. All right, now the next two are the only ones that we've got here that really take like different types of data types. The biserial, what this does, this takes one variable, which is going to be numeric. The other one is dichotomous, two levels, and then assumes that the dichotomous data is a binned normally distributed variable, then assumes that the numeric and the unobserved latent variable together are bivariate normal, then uses that assumption to get a maximum likelihood estimate of Pearson's correlation. Now polyserial takes ordinal data and a numeric data, assumes that the ordinal data is binned from a univariate normal, and that normal latent normal variable and the observed numeric together are bivariate normal, and then computes the maximum likelihood estimate of the Pearson correlation. All right, so these four you can call the latent correlations, because they're assuming that we have observed data, but that observed data is coming from an unobserved normal distribution. All right, so I'm going to go ahead. First thing I'm going to do is load some data so we can work on some examples. And so this is Longley's economic regression data. This is well known to have highly correlated variables in them. It's not a very big data set. Here are the fields. For our purpose, we just know that all of these are numeric variables. And here I went ahead and just did a pairs plot, so you can see that yes, we definitely have some correlation going on. And then I split the year into two different groups, the green and blue, just so that way, you know, as we look through here, we know which years are the earlier years, which years are the later years. Blue are the later years. All right, so Pearson's correlation. This is the standard classic correlation. When you hear someone say the word correlation, either they're using it colloquially and not mathematically, or they're probably talking about this one in particular. Remember that we need paired numeric data for this. We don't want to be running binary data, and we don't want to run this with ordinal data in general. Now, why is that? Well, because this is built up under the assumption that we have a straight line relationship between the columns of data. So, you know, from the mathematical buildup of Pearson's correlation, if you take like a theory course, you'll see that ordinal data and binary data don't make sense in this context. Now, my opinion is that for like model exploring, seeing what's going on, it's still okay to use Pearson's correlation for the purpose of exploring your data. It's okay to drop ordinal data and binary data into Pearson's correlation if I'm doing exploration. Now, why would I do it that way instead of the other ways? Well, Pearson's correlation is fast. If I'm working on a big data project, Pearson's correlation is going to be the fastest way to get through it. So what I do personally, if I'm working in a situation where computation time takes longer than I'd like, I'll just go ahead and use Pearson to give me insight into what's going on. Honestly, between Pearson's correlation, Spearman's rho, and Kindle's tau, you get pretty close results overall. Things will be in the same ballpark, but there will be a difference. Now, if you're going to go that route, I personally think that if you're going to step away from numeric data with Pearson's correlation, it's best to not report your results to your stakeholders because you don't want to be called out on doing something that is kind of hinky. And Pearson's correlation is an excellent choice if I'm doing linear regression because it's fitting that straight line relationship correlation. All right, so to do this, I'm going to use the core function. I'm going to say that the method is Pearson, and now I'm dropping in a numeric data frame into the data, and I'm going to get a symmetric matrix. I get ones on the diagonal. All the values are between -1 and 1. We've got a negative value, and so we can see that the Pearson correlation between GNP deflator and unemployed is 0.62. And just so that we get something a little bit more visual to work with, I went ahead and did a core plot using the core plot package. So core plot function with its namesake package. So first thing I pass in for that is going to be the correlation matrix, which is a symmetric matrix with all values between -1 and 1, and it's it's going to be it'll be positive definite also. Now here I chose ellipse for the visual presentation. So if it's narrow, I know that there's a stronger correlation. So I have a very strong correlation here. If it's wider, looks more like a circle, I have a weaker correlation. So here we have a weaker correlation between armed forces and years. Now the direction tells me if it's positive or negative correlation. Like here, this is going downhill from left to right. So this corresponds to a negative correlation. This is going uphill from left to right. So that tells me it's a positive correlation. So positive slope, just like in college algebra, negative slope, just like in college algebra. The next one we want to look at is Spearman's correlation. And so this is very similar to Pearson's, but first we take the data and we convert the data to its rank. And now if you're going to be using this, make sure, and you're concerned about it, check out how ties are handled in the calculations to make sure you understand what's going on in terms. Anytime you're dealing with rank, you need to know how the system deals with ties. This is honestly my preferred correlation measurement when I'm doing supervised learning, because this is a little bit more flexible as long as I have a monotonically increasing or monotonically decreasing relationship between variables. So if I had, like, let's say a curve like this, not a straight line, but a curve, Spearman's correlation will pick that up very nicely, while Pearson's correlation will come out low. And so I like this a lot because it's more flexible than Pearson's. It detects a wider range of geometric relationships. And the output is very similar when I set the method equal to Spearman. So I get a correlation matrix, and here's my plot. And you'll notice if you start looking through precisely through the output, the values are in the same ballpark as Pearson, and that's very common. I'm not getting anything like wildly different. Now there is a difference, so that's looking. I think it's looking a little bit darker than it was under Pearson's. In general, Spearman's will be larger than Pearson's. Now, Kindle's tau, what this does, this measures the concordance between the two columns of data. So I consider this a good choice when I'm building conditional probability models. Something I don't like about this though is that compared to the other two, this tends to take a longer time to compute. And if I'm at work, I need to be moving through things. I don't want to sit around for computations if I can avoid it. And if you look at the actual formula, which I skipped over here, it has a very combinatorics feel to it. And here is the correlation plot. And you'll notice it looks very similar to the previous two. Oh, something I did, I ordered these variables row and columns using hierarchical clustering. I find that this is a good choice for figuring out the relationships between the variables, especially if I have a lot of them to work through. All right, so now let's talk about the latent correlations. All right, so there's four that we're going to talk about. First one is going to be Terracork correlation, which handles two dichotomous variables. Then we're going to talk about Polycork, which handles multiple level ordinal data. And then we'll talk about biserial, which takes numeric and dichotomous. And then we'll talk about polyserial, which will handle numeric along with ordinal. All right, so Terracork data, what it's going to happen is that it's going to take, it will take data that has two levels, and it's going to assume that the data is the result of binning a bivariate normal variable. So when I say bivariate, there's two levels, two dimensions. And so after you do the binning, you get a 2x2 contingency table. All right, so it takes that 2x2 contingency table, and then the assumption of bivariate normality, and does a maximum likelihood estimate on Pearsons correlation coefficient. Boom. It's a lot going on, but it's good stuff, good stuff. And so here I'm going to go ahead and use the LSAT 6 data set, which is in the psych package, and we need to call Bach in the data function to get that. And so to get this, I just use the Terracork function in psych. And the actual values I want for this are row. There are some other aspects of the output that I suppress because I want to keep things similar to the other outputs we've looked at. All right, and so here I can get my correlation measurements. And so the LSAT data is all zeros and ones, by the way. And I can look and see that we have weak correlation between all the variables if I look through here. Next is Polycork correlation, and this assumes that we have pairwise ordinal data, and the ordinal data is a result of binning bivariate normal. So then, under the assumption that it's coming from bivariate normal, uses maximum likelihood estimate, and boom, gives us an estimate of the Pearson correlation. All right, so to get this, to give you an example, I need to have some ordinal data. You'll notice I have a 3x3 contingency table. What's going on is that this table, each row corresponds to a level of the ordinal data in the first variable, and each column corresponds to a level of the ordinal data in the second column. And now the dimensions don't have to match. They do here because I'm just trying to keep it simple. All right, so if I look here, this says that the first row, we see that the first variable had the third level 41 times simultaneously when the second variable had the first level. And so this here is implied that rows correspond to the first variable, columns correspond to the second variable, and those variables are ordinal. And so since I only have two variables, I can only get one correlation. and that is 0.49. We can see that there isn't much of a correlation going on. And here's some other diagnostic aspects that we can use. Now, by serial correlation, what this does, this takes a numeric random variable and then takes a dichotomous random variable and assumes that first and foremost, they originate coming from bivariate normal, that the dichotomous one is the result of binning the second dimension, and then under those assumptions goes through and calculates the maximum likelihood estimate of Pearson's correlation. All right, so just to show you what's going on, this is a simulation function. So we don't really care for this video what is going on here. We just care that this is our data, that I have, I get some data, and here's my data frame. The first column is numeric. The second one is dichotomous. And here you can see I'm just going true and false. Is it positive or negative or 0? And just to show you what it looks like, here is the box plot of the numeric values by the dichotomous variable that we built up. So true means that it's greater than or equal to 0 on the dichotomous variable. All right. So now if I run the biserial, I can see that the Pearson correlation estimate is 0.9. That's pretty strong. Now polyserial does the same thing, but what's going on here is that I have ordinal data instead of dichotomous data. So let's take a look at the box plots. And so here we can see that as we go through the different levels of the ordinal data, we can definitely see that the numeric values are increasing. So looking at this, I believe that there's going to be a pretty strong correlation. Now, something that's kind of a pain in the neck about this function, the polyserial function in the psych package, it wants X to be a data frame and it wants Y to be a data frame. And everything's pretty easy. It works out nicely once you do it, but you have to take that additional step of putting it in a data frame. And once we do that, we can see that we have a correlation of 0.92, which is consistent with our observations from the box plots. All right, well, that's all I've got for you. Take care and goodbye.